When is mechanical energy conserved? That's the title of this video, and that's a pretty hard question in mechanics, because basically the answer is, well, if you can tell conservative from non-conservative forces, and only conservative forces act, then mechanical energy is indeed conserved. So how do you do that in practice? Well, let's start with the idea of what is mechanical energy. It's kinetic energy and potential energy added together, and I'll write that as a mathematical expression in a little bit unconventional form, because I've indicated that generally speaking the kinetic energy is due to mass in motion, and so it's a function of some velocity, or maybe it's a function of omega, the rotational rate of some solid object. And of course that mass in motion can be used to do work. The second term is the potential energy. Potential energy, in its essence, has the potential to do work. If we have a large pond, a mill pond, filled up with water up on some hillside, we can hook a pipe to that and use the energy of the flowing water to do work whenever we want. It has the potential to do work, or we have the potential to convert that potential energy into the rapidly flowing water into kinetic energy. So in practice, we might take a different definition of non-conservative work from the formal one that I'm going to give you in a minute, and we'll simply say that non-conservative work changes the mechanical energy. It changes the energy of your system. So anything that changes your energy is non-conservative work, and therefore the final energy is equal to the initial energy plus the non-conservative work. Or, as you will write it out, the energy is kinetic energy plus initial energy, kinetic energy plus potential energy initially, plus the non-conservative work, equals the kinetic energy plus the potential energy at the end of the process. Now, we can think of this graphically. Here's your system in the middle, and it has a certain amount of mechanical energy. How can that mechanical energy get out? Well, the common way is if you have some kinetic energy, some object moving, friction or drag can slow it down. And that will result in turning that mechanical energy into heat. Another way to change the mechanical energy of the system is that it can interact with basically the world, or what some people call the environment. And the way that that happens most often is with external forces. Something outside the system pushes on it, accelerates a mass, or decelerates a mass, or compresses a spring, and all these things change the mechanical energy of your system, adding to it or subtracting from it, or transporting the energy out or transporting the mechanical energy in. Another common, usually a source of mechanical energy, are electrical energy and chemical energy. So these things, for instance, either electricity or chemistry or chemical reactions can power a motor. And that can transfer energy into your system. Also, they could mechanical energy inside your system could power a generator, so that could go the other way. Other examples would be muscles or an explosion, which would convert chemical energy into kinetic energy of the fragments or the two pieces that it blew apart. Now, notice there's a slight difference in the diagram between the world here, which I drew with a solid line to indicate that that is a physically distinct system from the system, the mechanical energy that we're talking about in our system. Whereas the heat and the electrical and chemical energy, I just drew dashed lines around, and that's to indicate that they might be inside your system or they might be outside of your system. The heat could be just from two objects rubbing together within your system, or it could be because your system rubbed against some rough surface like a road. And in the first case, it's obvious the heat's going to be inside the system, but in the second case where you're rubbing on the road, some of it might be transferred to the road and some might stay inside your system. It's very difficult to tell. the same thing is true of electrical and chemical energy. You might have a battery inside your system that runs a little motor inside your system, or the chemicals could be inside and something inside your system could blow up, or it could be that there are wires that bring electrical energy into your system. But the key point is that the mechanical energy can flow into or out of your system. Now, the definition of non-conservative work is that if you go around a closed path, then when you come back to the same point, you have a different amount of energy. So an example of that, well, a mathematical expression for that, is that the work around a closed path here, and these should be vector signs, of F dot dr is not equal to 0. So let's give an example. Let's just say we had a block and it has some friction, so it goes on a rough surface, and it travels a distance L. Now, during that travel it has some force acting on it, some friction force, and so the work is equal to minus FL. And now the block's down here. So then let's say the block goes back the other way. So at first it went down that way, and now it goes back this way. Well, when it goes back, the friction force is acting against it again, and so the work is again minus FL. So the total work for this process, which gets the block right back to where it started, in other words, goes around a closed path, the total work is equal to minus 2FL, and this is obviously therefore non-conservative work. Now let's talk about how you deal with mechanical energy in practice. The practical definition of conservative forces might somewhat cynically be taken as, well, in my mechanics course I'm probably only going to treat gravity or springs with potential energy, and we're going to treat those two things as conservative energy, and everything as conservative interactions, and everything else is going to be non-conservative. Treating those two forces or those two interactions as conservative forces leads to a conceptual as well as a computational simplification, because it means you don't have to calculate the work from them. You put the idea of conservative forces or conservative interactions, you don't treat the force, you just treat the interaction by accounting for it using the idea of potential energy. So, and then you remember, of course, that only non-conservative work changes the mechanical energy. And one other point here that I should make is that the work is a function of the initial and the final position, and also the detailed path that the system traveled from initial state to final state can change the amount of work, non-conservative work that is. So let's just summarize of conservative versus non-conservative interactions. For conservative interactions, well, first of all, if it's gravity, universal or just a constant local gravity, or if it's a spring, you're probably going to treat it best with conservative ideas and incorporating it into the potential. If you have a string that connects two blocks inside your system and it doesn't stretch, then that'll be conservative. Or so will a normal force. If an object is on a flat table, the normal force doesn't do any work on it if the table is stationary. Or if it's going around a curved track, the normal force of the track doesn't do any work on the object because it's perpendicular to the direction that the object's moving. And another point about conservative forces or conservative interactions is that they can change kinetic into potential or potential into kinetic energy. And most important, conservative interactions keep mechanical energy constant. Now let's look quickly at some characteristics of non-conservative interactions. Well, first of all, friction, drag, some external push or pull on the system, they're bound to be non-conservative. And if the work depends on the path, as we've mentioned, that would indicate that any force is non-conservative. Practically, though, what we'll look for is whether the process can transfer energy into or out of the system, especially kinetic energy out of the system in the form of heat or or out of mechanical energy into heat. Even if the heat is inside the system, it still reduces the mechanical energy of the system. Or if chemical energy or something else will convert into kinetic energy or potential energy inside the system, those interactions are non-conservative. And finally, when we have just conservative forces, then it's almost always best to represent them using the potential energy to account for those conservative interactions. And of course we get back to the same formula that we discussed before.